Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series intended for the BSc Physical Sciences students who are doing the paper on applied electronics, and we have been seeing a course of lectures on quantum mechanics, and in this lecture we will have the contents as follows: hydrogen atom problem, Schrodinger's equation, input the potential, method of separation of variables, boundary condition, outputs, eigenvalues and eigen functions. You all know that the hydrogen atom problem was discussed by Niels Bohr. According to Niels Bohr, the electron was considered as a particle having a definite mass, and it was assumed to revolve in a circular orbit. You got a proton here in the hydrogen atom, and the electron is here at a definite distance, say separated by r, the distance separating the nucleus or the proton and the electron having a mass m, the distance is r, and the electron here is revolving in a orbit according to Niels Bohr. The essential point is electron is considered as a particle, and now we are going to discuss the same hydrogen atom using quantum mechanics, not using the quantum theory or the Bohr atom model. The Bohr atom model, as was discussed by Niels Bohr, the one that we are going to discuss now and the results which we are going to arrive at will be somewhat different, or new things will arise from this discussion. This particular problem, hydrogen atom problem, is a very simple problem in the sense it is a two body problem. You know, the proton here and the electron here, only there are two particles. If you go to some of the other atoms, there will be many electrons, it is called a many body problem, but here we have got a two body problem. So, the potential that we will be obtaining will be exact. So, the problem can be exactly solved, because it is two body problem. It is a very important thing. The problem can be solved exactly without approximations. It is a two body problem. So, the potential energy will be the input, as I told you in the last lectures. In quantum mechanics, the input is the potential energy. For any problem, potential energy is the input. If you look at the Schrodinger equation, the input will be the potential and the outputs are, what are the outputs? Now, by now you should remember the outputs that you will be expecting from the Schrodinger equation. They are what? The eigen values and eigen functions. the energy eigenvalues and the eigenfunctions. That is, eigenfunction means what? Here it refers to the state of the electron. So, the potential energy will be given as 1 by 4 pi epsilon naught into Z e square by r. In the case of hydrogen atom, Z is 1. So, it turns out to be E square by r. Z e in general is the charge of the nucleus and E is the charge of the electron, and we also now talk about the reduced mass mu, that will be the product of the mass of the electron and the mass of the nucleus divided by the sum of the two masses, that gives what is called the reduced mass. And we write down the Hamiltonian in any quantum mechanical problem. If you use the Schrodinger equation, what is Schrodinger equation? You write H operating on psi is equal to E operating on psi, or H operating on psi is E multiplied by psi. E is what? The eigenvalue. H is the Hamiltonian operator. The operator operating on a function gives a constant times the function. So, that constant is the so called eigenvalue. H is the Hamiltonian operator. What is the Hamiltonian operator? It is sum of the kinetic energy parts and the potential energy parts. You know, in quantum mechanics, you replace the variables or observables by the operators. The kinetic energy operator is nothing but h bar square by 2 m. If m is replaced by mu, the reduced mass, obviously the kinetic energy operator will be minus h bar square by 2 mu into del square. What is del square? It is a Laplacian operator. So, the first term refers to the kinetic energy part, it is operator, formalism, the kinetic energy part. The second term obviously refers to the potential energy part. So, sum of the kinetic energy part and the potential energy, it forms the Hamiltonian. You write H is equal to T plus V, that is the T is the kinetic energy part and the V is the potential energy part. It is difficult to solve the equation. You have your H operating on psi will be equal to E into psi. You have to obtain E and psi, that is the objective of the problem, by but solving the Schrodinger equation by expressing del square. What is del square? The Laplacian operator del square is nothing but dou square by dou x square plus dou square by dou y square plus dou square by dou z square in the rectangular coordinate system. But the problem will be difficult if you use the rectangular coordinates. Therefore, you express del square in terms of spherical polar coordinates, namely r, theta and phi. This r, theta and phi will be these angles. R is the distance that separates the proton and the electron, and the other angles are shown in this diagram. This is theta and this angle is phi. So, this angle phi here, this angle theta here, the r. So, therefore, you express del square in terms of r theta phi. There is a standard expression that is expressing del square in terms of r theta and phi. If you do that, your del square will be the Laplacian operator can be written in terms of r theta phi. When you do that, that will be equal to 1 by r square dou by dou r into r square by dou r plus 1 by r square into sin theta into dou by dou theta of sin theta dou by dou theta plus 1 by r square sin square theta multiplied by dou square by. This is the Hamiltonian operator that consists of the kinetic energy part. So, you have the Laplacian operator del square expressed in terms of the spherical polar coordinates r theta and phi. Instead of x, y, z, we express in terms of r theta and phi. So, del square in terms of r theta and phi will become equal to 1 by r square dou by dou r of r square into dou by dou r plus 1 by r square sin theta into dou by dou theta of sin theta dou by dou theta plus 1 by r square sin square theta into dou square by dou phi square. That is expression for del square, the Laplacian operator that operates upon the wave function psi. You see here the whole thing, you have got the Laplacian operator, then that is the kinetic energy part, right. Then the potential energy part comes here, right. You look at the expression once again, you have got a del square here, del square has been replaced by an expression of this kind, wherein you express del square in terms of r theta phi. Therefore, when you substitute this expression for del square, the whole thing will become of this kind. Of course, you will be having h bar square by 2 mu outside, then del square, right, in terms of r theta phi. This del square operates on psi, then the potential energy also will be multiplied by psi, that gives the E into psi, that is the Schrodinger equation. What is Schrodinger equation? H, the whole thing is H, right. You remove psi, the entire thing that you got here is H. H operating on psi will be equal to E into psi, that is the Schrodinger equation, right. As I told you, the input will be this part, the potential energy part will be the input. The outputs that we expect are the energy eigenvalue E and also the eigen function. What is the eigen function? It gives the state of the electron, right. It gives the state of the electron, and you saw in the last lecture when we applied the Schrodinger equation for the particle in a box, you saw that the energy eigenvalues get automatically quantized. Automatically quantized means the energy is expressed in terms of an integer n, that integer n comes automatically. What do you mean by saying that the integer n comes automatically? Through the introduction of the boundary condition. Unlike the Bohr atom model or vector atom model, wherein we introduced various quantum numbers, you saw the Pauli exclusion principle. We talked about the principal quantum number, the orbital quantum number, ML, MS and so on, very many quantum numbers in the vector atom model. These quantum numbers in the development of atomic physics were introduced arbitrarily in order to improve our understanding of electrons and atoms, but here it is very straightforward based on the postulates of quantum mechanics. There is no ad hocism, you do not introduce any of the quantum numbers in a ad hoc or arbitrary manner. So, based on the postulates you develop the understanding of electrons and atoms. The simplest atom is the hydrogen atom. You want to determine the energies that the electron, the lone electron in the hydrogen atom can assume, and also the eigenstate, that is the probability of finding the electron at a given point. You all know psi is a thing which cannot be measured in a laboratory. What can be measured is psi star sign, that gives the probability density, the probability of finding electron at a given point at a given instant of time. So, these things could be obtained, ought to be obtained, that is what the aim of this lecture. Both the left hand side and the right hand side contain a term linear in psi. So, by combining these two you can have an expression of this kind, right. You have your 2 mu by h bar square into E times E plus z e square by 4 pi epsilon naught into r into psi. Okay. Then a very important step is the following. In order to solve the equation that we saw earlier containing r, theta and phi, you make use of the method of separation of variables. The variables r, theta and phi are mutually exclusive. By this what I mean is r does not depend upon theta, theta does not depend upon phi. Therefore, the entire equation can be put up by method of separation of variables. What we mean is the entire equation can be split up into the radial part and the angular part. You can split up the whole equation into 3 equations, one depending upon r, the other 2 depending upon theta and phi respectively. Therefore, you write down the wave function psi, psi in terms of r theta phi can be written as the radial part r depending upon small r as a function of r, and y as a function of theta and phi, and this y is called the spherical harmonics. I will discuss more about the radial equation and the angular parts after the break. We will have a break at this point. Welcome back at the break. As I told you, the Schrodinger equation, which is made up of r, theta and phi, can be solved by the method of separation of variables, wherein we separate the equation into 3 equations, one involving r only. It is called a radial part of the Schrodinger equation, the other involving theta, the third one involving phi. The one involving phi will be very simple, as very simple, and the wave function which is written as psi r theta phi can be written as r as a function of r, that is called the radial part of the Schrodinger equation, that is a radial solution. Then y theta phi, that is called a spherical harmonics. You can have a suffix Lm, the quantum numbers L and m will be also coming into the picture, they are called as spherical harmonics. Since the angular part is nothing to do with the radial part, or y does not depend upon r, we can move it in front of the radial derivative. Therefore, you can write dou psi by dou r as dou by dou r multiplied by r into y. Y does not depend upon r. Okay. So, y into dr by dr, because you are taking the differential of r with respect to small r. Therefore, you write y into dr by dr here, y is taken to the front or the left of the equation, because y does not depend upon r, okay, the angular part. So, also r does not depend on the angular variables, thus replace psi and the differentials. So, you have the equation in this form, y divided by r square dou by dou r of r square dou r by dou r plus r by r square sin theta dou by dou theta into sin theta dou y by dou theta, y is the angular part, right, plus r by r square sin square theta into dou square y by dou phi square plus 2 mu, that is the reduced mass of the electron, divided by h bar square into E plus E is the eigenvalue plus z e square by 4 pi epsilon naught. What is epsilon naught? Is a permittivity in free space multiplied by r into y. Okay. That is the equation that you got. This equation can be, now you can multiply by r square and divide by r into y to separate the radial and angular terms. Therefore, the equation can be rewritten in this form, 1 by r square dou by dou r of r square dou r by dou r plus 1 by r square sin theta dou by dou theta of sin theta dou y by dou theta plus 1 by r square sin square theta into dou square y by dou phi square plus 2 mu by h bar square plus you got E here plus z e square by 4 pi epsilon naught into r is equal to 0. You should note that the first and fourth terms, they only depend upon r. You see, the first term depends upon r. This also depends upon r, whereas this depends only on theta and this depends only on phi. Okay? That is important thing. Okay? This depends upon r, this also depends upon r. Therefore, I write the first and fourth terms depend on r only, the middle terms depend on the angles alone. They can balance each other for all points in space. That means, for all values of r, if the radial and angular terms are the same constant, but with opposite sign. Hence, I can write the radial part is equal to 0. So, dou by d by dr of r square into dr by dr plus 2 mu by h bar square into E plus z e square by 4 pi epsilon naught into r minus a r is equal to 0. So, that contains what? The essence of the thing is this contains only r. So, this is the radial part of the Schrodinger equation. What I have written is, I have written that part of the Schrodinger equation which involves only r. What is r? R is the distance separating the electron and the proton and the hydrogen atom. Okay? That is the radial part of the Schrodinger equation, whereas the angular part is given as follows. This depends upon theta and also phi. You got phi here, theta here, right. Therefore, the angular part of the Schrodinger equation will be 1 by sin theta dou by dou theta into sin theta multiplied by dy by d theta plus 1 by sin square theta into dou square y by dou phi square plus a y. So, this refers to the angular part, this refers to the radial part of the Schrodinger equation. So, we now talk about the r equation. What is r equation? The equation containing r. So, I am now talking about this equation, r equation, that is the radial part of the Schrodinger equation. The value of A that you have here is found to be, I will not go into the details, I am not supposed to go through the details, because these equations, unlike what we saw in the particle in a box problem, they are much more complicated, containing Legendre polynomials, Laguerre polynomials and so on. So, without going to the details, you can safely say that the value of A is found to be L into L plus 1, where L is an integer. What is L? L is the orbital quantum number which you came across in the vector atom model. In the radial equation, you have now d by dr of r square dr by dr plus 2 mu into r square by h bar square into E plus z e square by 4 pi epsilon naught into r minus L into L plus 1, that is what you have here, right. That is what I have done is, I have substituted for A now, L into L plus 1 multiplied by r is equal to 0. Okay. Apply the product rule to the first term. By this, what you get now is r square into d square r by dr square plus 2 r by dr plus 2 mu r square by h bar square multiplied by E plus z e square by 4 pi epsilon naught into r minus L into L plus 1 into r will be equal to 0. That is what you finally arrive at for the r equation. You divide this equation by r square. So, this r square will go and you got r will come to the denominator. Therefore, you have r in the denominator in second term. This r square has been removed now, you have got d square r by dr square. Therefore, by dividing the previous equation through by r square, you arrive at an expression of this kind, let me now read d square r by dr square plus 2 by r into dr by dr plus 2 mu by h bar square into E plus z e square by 4 pi epsilon naught into r minus L into L plus 1 by r square multiplied by capital R will be equal to 0. We can't solve this equation straight away, but for very large R values the highlighted terms are forced to 0 because they go to replace reciprocal with R. What I mean by this is we talk of the asymptotic solution or the asymptotic equation. Physically what I would like to tell you is you have got the proton here and the electron is found here. Now, I am talking about the boundary condition. Now, what is the boundary condition? You have studied the boundary condition applied to the problem of a particle in a box. Now, we go to the boundary condition in the case of electron in the hydrogen atom, electron and a proton. You have got a proton here, the electron here, and I ask the question, if I write down the wave function as e to the power of plus or minus alpha r, I will repeat again, I write the wave function psi of r as e to the power of plus or minus alpha r. Which one will you take as the acceptable solution or physically meaningful solution, either with a plus sign or minus sign? If you assume the solution with the plus sign, you have psi is equal to e to the power of plus alpha r. Plus alpha r means what? When r becomes larger and larger, psi will increase exponentially, right? It is e to the power of plus alpha r, plus alpha x or alpha r. Therefore, when r increases, psi will increase. That is unphysical. It is a physically meaningless solution, right? Physically unacceptable solution, because what is psi? Psi cannot be measured, as I told you, psi star psi alone can be measured. That gives the probability of finding the electron at a given point. If you have got a proton here, the probability of finding the electron cannot be cannot go on increasing, right? Cannot be increasing forever. You cannot have the electron here, proton here. I cannot say the probability of finding the electron will be at a distance of 5 kilometers. You know, the hydrogen atom is so small, around 0.5 angstrom unit. Therefore, it should the wave function should vanish exponentially. It should have exponentially. It should be an expression with a negative sign. Therefore, you write psi of r as e to the power of minus alpha r. That is the so called well behaved wave function. If you take with a plus sign, it is called a ill behaved, unacceptable, physically meaningless solution, because it will give you the probability of finding the electron at a far off place to have a higher value. On the other hand, the wave function should decay exponentially. The former one will lead to what is called infinity catastrophe. It will say at infinity the probability of finding electron is large, which is unphysical, because hydrogen atom has got a finite size. Therefore, the wave function should be exponentially decaying. Now, these things are taken care of here. So, the above equation leads to an asymptotic equation of this kind, d square r infinity is here by dr square plus 2 mu e by h bar square, or infinity is equal to 0. The solution is given as follows. You got r infinity is equal to C 3 plus into exponential of I into square root of 2 mu e by h bar square multiplied by r plus C 4 into exponential of minus I into 2 mu e by h bar square within the square root multiplied by r here. Then it makes sense to use as the 0 point of potential energy, the energy of the free electron In the asymptotic case, E tends to 0 for an electron far away from the nucleus, as it is practically free. Since the presence of positive charge in the nucleus stabilizes the atom, we must look for solutions where E becomes negative and the electron comes closer to the nucleus. You know, the energy of the electron should be negative. Negative means the electron is bound to the atom. In physics, you know, the negative sign stands for attraction. The binding energy should be negative. These two conditions are met if we choose C4 is equal to 0 and we use the fact that E is less than 0, it should be negative to get rid of the imaginary unit. So, E should be negative. E is negative means you are talking about a bound state problem. The electron is bound to the proton. Okay. So, the asymptotic solution is then, or infinity will be C3 multiplied by a factor of this kind. The detail near the nucleus is expanded in a power series of this kind. So, we have been discussing so far the radial part of the Schrodinger equation, which will ultimately give the so called eigen values, and of course, we have to get the eigen functions also. The eigen functions refer to the state of the electron in the hydrogen atom. Now, we will move on to the summary part of this lecture. It goes as follows. One of the postulates, one of the first problems which was tried employing quantum mechanics was the hydrogen atom, as it was the simplest atom. The input is obviously very simple. It was a two body problem which could be exactly solved. The problem is greatly simplified by expressing the Laplacian operator in terms of radial and angular parts. The boundary condition decides the eigen values and eigen functions. It should be realized that the principal quantum number n automatically comes out from the radial Schrodinger equation. The questions are, what do you understand from the statement that the hydrogen atom is a two body problem and hence is exactly solvable? Write down the Schrodinger equation in terms of the radial and angular coordinates. What is meant by the method of separation of variables? Give the eigen values of the hydrogen atom and compare it with the one derived by Bohr. With this, we come to the end of the lecture. The rest of the things we will see in the lectures to come. Thank you.